Yesterday, Tom Eagar covered some of his philosophy about engineering and how to make your bus useful, happy, and how to be useful. He's going to come back next week and talk a lot about forming, metal forming. And I'm there to cover kind of the other half of the story where at the end of the day, if you beat the metal or you make a plastic piece, you have to make it so you really meet the criteria for the application. So we're giving you guys actually a very broad class, but it's close to what we do day in, day out as far as consulting and some of the failure analysis work we do. So that's a little bit the idea, to give something to every one of you that is both about how to make it, but also how to make it so it meets the customer expectation, it meets the demand on the market. And obviously, when we talk about on the graph here about the capacity exceeding the demand, we can talk about a lot of different things. There are a lot of things you need to think about if you're going to achieve that goal. So I brought a ski. This is the good side with the front binder here that's complete, and this is the one I broke just 2 weeks ago. So whoever came up with the specific design here, because what you need in the binding is you need to be able to rotate. So if you fall, the boot comes off. And to do that, you have a spring that's preloaded right here in the enclosure. So when you turn, the spring gets compressed up until you reach the critical point on the rotation, and now it gets easy again. So as an engineer, I looked at this and said, oh, it means the plastic had a load all the time, because the spring was preloaded when I had it in my garage or anywhere they were for the past little while, and we can talk about that. So I already know from the beginning that this is going to see impact. It's also going to see constant load, and then there's all the aging associated with it. The plastic will lose some of its ductility over time. It is subject to degradation. They put a lot of additives in some of the plastics, especially the polyethylenes, but these have a useful life. At some point, you consume all of them, and then you have degradation. So this binding was 20 years old. So we don't have to go through the details about what happened. It's just the resin was not built for that long. So I reached that limit on this capacity-demand ratio for really the integrity of the resin. It wasn't so much that it deformed and changed its shape. It's really that it's not the plastic today that it was 20 years ago, just because of UV radiation and time by itself. So that's in a nutshell some of the things that needs to be thought about, not only for sporting goods, but everything that's built. Sometime if it's a metal, it's corrosion that also needs to be taken into account. And some metals will have all sort of incompatibility with certain environment in processing plants. So it can become brittle in a certain range of temperature. So you will think you heat a piece of steel, it becomes softer, but that's not always the case. So anywhere you go, you have to think about multiple aspects of the material that could limit the useful life. So I wanted to point you out to a very useful database that's on the MIT library where you can access, I'm not kidding, between here and here of handbooks, searchables, and you have images. So even if you're thinking about your project, regardless of whether it's a design manufacturing project or a life assessment project, the 20 handbooks are called the metals handbooks, and they cover forming in different forms, sheet forming, forging, heat treatment. There are some handbooks more on properties if you decide to include some material selection in your project. It's a great reference. You can also find it in the library, but sometime if you're working on a homework or between classes, if you're thinking you want to learn a little bit more, like if you want to learn a little bit more about what I'm going to be covering, the section 2 of volume 10 is helpful because it talks about the different criteria. Sometimes you'll design like a ski, the binding we talked about. I'll design it as good as the other manufacturer so I don't get in trouble with it. And it's done a lot, whether it's kind of by trial and error or it's under a specific standard, like in the aerospace, there are a lot of standards. So really, depending on what you're building, it's really something to think about. What's going to be the acceptance criteria? What do you need to achieve in terms of reliability? In terms, the cost is always a question, and we talked about that yesterday. Despite cost, if you don't want to get in trouble, if you want to make sure you meet all the requirements, you have to look at different technical aspects and evaluate it as far as what's the probability of a failure and is it acceptable. Some failures may be okay, like my bindings. I was trying them out on top of the slope. The ski just left, so I just had to take the chairlift back. Now, I'll look funny, but that's what happened. All right, let's pull this up. So you all familiar with the library databases? You do any search there, and you'll come up with what's called the ASM handbooks online, and that's where I said at least 20, and you have some extras now for plastics and composites. So here we can go all over the place between the different parts of engineering that come into making a product. But I thought I'd put them in some kind of a chronological order. So you select and understand the material, then you have to put it into shape or join it, and that's covered a lot in this class. You have to have some dimension tolerances, some property requirements. We call them specifications for what you're going to build. So if I go to a shop, I ask somebody, so what are you building? Normally they'll have a print. It says, I'm using this material to this dimension, and I do it in such a way. Now, at some point, the design and life assessment comes in to make sure that this print somehow will be acceptable on the market or in the factory or whatever you're building in the building. And that's a difficult part because there are different ways to do it. I mentioned about doing like the others. I mentioned about standards. And you can do it if you're building special structure for NASA. You probably don't have any reference, so you're going to do it based on what you know. You may still do it based on what other people have done in the past, so from experience. And after you've done with all this, as engineers, you want to do a certain form of validation. And sometimes the validation is a calculation. A lot of times when it's in a critical application that you have multiple products built the same way, you will build them and test them in actual conditions, or in accelerated testing when you make the conditions worse than they are in reality. And one example of that are aircraft fuselage, where you take the wing in rest position. If the designer says, well, worst wind, it's going to bend up like this. Well, in the factory, we go up and bend it really all the way, sometime until the point we start breaking parts or deforming parts heavily, and sometime to a point where you can't use it for future flights, but you can still land with it. So that's the idea behind knowing what's your limit and what kind of a safety factor you have and what's acceptable when you exceed the limit. So that's really dependent on the application. In elevator, for example, elevator systems are typically behind the scene. You don't see them, and therefore you can say, well, after so many hours, maybe the cable comes off the door, so I know I got to do something about it. So that's not going to happen. So you need a higher safety factor, because you're not going to be willing to spend as much time as in aerospace, for example, figuring out if you have damages after using it. So there are a lot of criteria that comes into selecting the design, and it's very specific. It's not the purpose of the class to give you a prescriptive approach, but we'll definitely try to cover a variety of examples so you have an idea. When you are faced with a situation, you have some ideas what to look for. Is there any standard I should be following here? What else may happen in service that I haven't taken into account? Is it a problem? Type of approach. Okay, we will talk specifically about creep, fatigue, and overload fractures, and I'll give some examples. Given you guys' level, you must have heard of it, right? Everybody's heard about creep, mechanical creep. Okay, fatigue, mechanical fatigue. Okay. And we'll talk at the end a little bit about how it relates, how the materials aspect relate here with those failure mechanism with respect to forming and joining of materials. So creep here is essentially, and I thought I would do it on the board. So say I apply a load. So it's a constant load. So put it 500 pounds on a specimen on my little thing here for the binding. What happens is over time, and I should do it separate. So this is time in both cases. And now I'm putting the deformation, which is essentially the elongation divided by the original length of the sample. And initially, when I apply the load, I have a certain amount of deformation that's given by the elastic constant or Young's modulus, and you're all familiar with that. But after that, over time, you'll have a continued deformation that will typically slow down. So in there you have a viscoelastic response, and then you have a viscoplastic response. So it keeps deforming, and even if on my plot here looks like it's going to a plateau, what you're seeing on the screen is a log scale. So it goes from minutes up until 50 years on the same plot on a logarithmic scale. And you can see there that as far as the plastic goes, in this example, at ambient temperature, it keeps deforming. As long as you have load on it, it deforms. And depending on how much load you have, and these are the different green curves, you can have a failure in creep, or you may have a useful life. And there's a big distinction between them. So some of the red curves here, looking at the lower one, it's only 5.2 megapascal as opposed to 12 megapascal for the highest one on a plastic that could be approximately 30, 40 megapascal of yield strength. So it doesn't matter too much what the yield strength is if you're going for a design like this of long life. What matters is how you're going to evolve in terms of deformation and ultimately fracture in a long-term application of approximately constant load. And we have an example of that, and I'll circulate it. This is a CPVC plastic pipe. It's used for fire suppression systems. So it's at relatively high pressure, maybe 150 to 200 psi, so about twice what you have in potable water. Now there's one side that's flat. That's a cut that we made to see half of it. But the upper side, what you see are a lot of small cracks, and probably you'll see the groove from the inside out, and resulted first in leakage and eventually an overall burst of the pipe. So it does happen. A lot of times it happens because you have a bad overall combination of conditions. So it's not necessarily just, oh, in this building it was a little bit warmer, or, well, the pressure was a little bit too high. So you have more than one of those variables that comes into play. And for those plastics, unfortunately, also contaminants make a big difference in help creating the little cracks. But the overall process remains that you don't know anything about whether you have damage that's being created unless you go and look for very fine cracks. There are other cracks very close to the one that you see there, and they're visible because there's a black discoloration. But most of the time, it's in the inside of the pipe. There's no easy way to find out that it's there. But it happens under constant load, the creep, and it's slow. The first step is you deform, so you grow the diameter in the case of the pipe. Eventually you start a crack. The crack's going to grow slowly. In this case, it did grow all the way through the thickness before you had the final burst.
Can I ask a question about that?
Yes.
Do you know, does the orientation of the pipe matter? Do these cracks begin on the top or the bottom?
Sometimes they do. It's a very interesting question. My comment would be that it's very unfortunate for those pipes that the hoop stress is, all around trying to grow it. It's about twice as much as the longitudinal stress, and the extrusion direction makes it stronger in the longitudinal way. So I'll detail that to make sure we cover this. It's the most important aspect here. So I'm doing an extrusion to arrive to this pipe. I start with more or less of a bulky piece of plastic. And it goes through a certain amount of dyes, and we're not going to go through the details of what they are for now, but you need to extrude, so you need a hole, create a hole in there, and eventually what you go about is you elongate the shape. And that's not only true geometrically, you create a molecular alignment of the polymer. The polymer really has very long chains, and you end up with chains that are more in this direction, longer in that direction, than in this direction. So when I come and I try to propagate a crack through a material that's essentially a line, it'll be much higher to do it this way, perpendicular to the chain, than if I try to go in between them. And that's why there's no question that it's always going to be a longitudinal crack, unfortunately, unless there's really something about the joining, something about local loads that create condition where you crack transverse. So you're going to crack in that direction. And so to your question, with respect to, we call it the Kluck position around the circumference of the pipe. So is it going to be on top, so we have 12, or bottom 6? Sometimes it matters and sometimes it doesn't. And I'll tell you even why. Is if you have a certain amount of contaminants in the system, having more of it doesn't make a difference. It's a little bit like a catalyst. And therefore it becomes relatively well distributed all around. In that example, I don't remember if it was the bottom. All right, so any other questions? If I keep saying a word you don't understand, please interrupt me. There's nothing wrong with that. And if you think it needs clarification, I'd be happy to pick it up. Fatigue is very similar to what we had up there, and therefore I'll reuse it. Except now, instead of having a constant load, I have a fluctuating load. And there are different ways you'll fluctuate the load. But that's the way I used here. And then you can count either half cycles or full cycles, depending on how to do it. And you can have it with what we call a mean load. It's still 500 plus or minus a certain amount. Or sometime it'll be 0 plus or minus a certain amount. So this creates the same amplitude, except that the mean load is close to 0. And we call that the loading ratio. It's coming in most fatigue books will give you R, which is the minimum over the maximum. That's all there is to it. It's only helpful if you're really trying on a chart to figure out if the fatigue data that you've been given is any relevant to your application. So that's where this comes in. If we have the sprinkler pipe that we talked about right here, the pressure fluctuation would be day and nights or turning on and off the pumps. So you'll have a relatively high minimum stress, not too far from the maximum stress. So it'd be close to 1 here. So it'll be, let's say we'll point it 0.75 for our reference. And when it's varying like this, it's -1. And that's a standard, if you will, for some of the measurements. There are other standards, but it goes typically from -1 up to a certain amount, close to 0.75. So we cover the range here. Good. Those curves that I've put on the slide, just examples to show you, these are plastics, that plastics will have different strength in a long-term application. And some of the common one, polyethylene and polypropylene, are not really the best one, but they have other advantages in terms of forming, in terms of cost, so they're still and density, so they're used a lot. But you can see that you can't go just by cost. If you have an application that's a little bit more demanding, some of the components inside the cars close to the engine, they'll go to a nylon type material as opposed to polyethylene and polypropylene because of temperature. Otherwise, they'll have to make it too big, for example. So it's not necessarily fatigue in that situation. It's more the creep resistance at temperature. But it's to give you a flavor. This is not, I didn't magnify the scale. I didn't show you from 40 to 50. It's really from 0 to 50 that you have this range of resistance of those different plastics. And the example is for fatigue, but it's the same effect for creep. There are a lot of difference. And then they also have different resistance to the environment sometimes. Gases. So now we're back to what you're probably most familiar with, stress strain curve. And I bring it in at this point because it is a form of overload fracture, right? You take the sample, typically in the laboratory, you pull on it, you start deforming it, so that's the yield stress. You keep deforming it, so now we're in the uniform strain region, this one here, and it will harden, typically. Both plastics and metals do. You reach a certain apparent maximum. And I want to be very clear about that. It's only apparent. It means at that point that you're starting to form a neck, but it doesn't mean that the material itself is becoming any weaker. It actually keeps getting harder and harder as you keep deforming it. But now, instead of deforming everywhere, you lost your section. So this curve here of engineering stress is still based on the original area, but now your area is reducing fast. And that's why we have that appearance. So I want to make that distinction because I've heard yesterday there were quite a few civil engineers, and I work with civil engineers. They see a stress strain curve, they look at the elongation at break. If it's 25%, they think it's important. That the value of 25 is very different from 22 or 28. Or at the end of the day, that value of elongation, when you reach this point at the fracture stress, is a combination of what your specimen is. And also, obviously, you're hardening. The more you harden, the more you'll be able to deform, stretch before you get to that neck. But if I take a thin specimen, it will start necking more slow, of the same material, it will start necking more slowly than if it's a good, round, big piece. So all those values, the fracture stress and the elongation at break that we talk about a lot, are not intrinsic material properties, we call. They are engineering data that we can use, but we should try not to overuse it. We should try to understand what's beyond it. And this relates to deformation, so I'm going to defer on the details. I don't want to leave you with an incomplete description. But for now, I think the idea is, if I take a specimen in the laboratory with that constant section and I pull on it, it's different than in other applications. For example, here, I'm going to pass on those screws. If we had done the material test on those two screws in the laboratory, we would have gotten a stress strain curve with maybe 20% elongation. I'm making up the number. I don't know exactly what it would be, but a certain elongation. But if you look at it, the way it broke, there's no elongation. And then the question is why? Well, it could be a multiple reasons, but one of them is you have these treads here that act as stress risers. This is another stress risers from any elementary class. If I have a hole in a plate, the stress around here is going to be 3 times what it is, far away when I'm pulling. If you have a notch on the surface, which is what we have here, it's going to be even higher factor. So what I have is actually something like this with a small radius and goes the other way. So I'm making a screw here. I'm going to say 5 to 10, depending on what the situation is. So that's really where the question of whether you have a ductile material or a brittle material comes in. When you are in a constrained situation, and we see that that fastener that was holding my my gutters when we had the snowstorm last year. It really didn't do too well. It didn't neck, and therefore all the information from the stress strain curve is useless. We have to go to another level, and that's what we'll cover next week. Another example where you can't use the stress strain curve the way it's set up. Let's see. I use these. If I have a detail where I managed to get the material to work in shear, and the way I do that a lot of times is what we call gusset plates. Oh yeah, civil engineers, so I have to be careful. You guys know all about this. So I put a plate, and then I have a member coming in, say, we'll do it to here. Simple one. So the load is being transferred here between a round tube and a gusset plate, and then it's connecting to something else. What I want to emphasize in this situation, it's a shear interface, and you don't have the stress risers, and you don't really have the tension either. So in this condition, you'll expect much more than the 20–30% elongation that you get in a tension situation. You may reach 60–80% deformation. So it becomes close to what you have in deformation processing of metals that we're going to cover in this class. But it shows you that a deformation fracture by overload in this condition is much harder to reach than it is in any other type of application. Actually, a shear fracture takes a lot of deformation. Now that you all seen the pipe, this is what the creep fracture looks like in the microscope. So here we have the inside of the pipe. And when I said we have multiple cracks, it's because I see this little half circle shape here. So there was an initiation close to the middle of this going in different directions to reach that boundary. So at some point in time, that's where the crack was. And then there was another one next to it that was actually a little smaller, and they shared that little ridge here. So that's how I know we had a lot of different cracks that started at the same time, which tells us that we really have a problem. Either there are a lot of impurities in the plastic, or we have too much load. So as soon as you load it, it starts cracking. Another example here is a shaft for a sport boat to go in the ocean. That was a side project a couple of years ago. Somebody came, said he lost his prop after using the boat for 200 hours. And he was very upset about this. He wanted to know what was going on. It's a very fancy piece of equipment. It's an Inconel, about 6-inch diameter shaft. And the question was, what happened from him? So I had to find out a little bit more about what he was doing. I asked him if the prop was balanced. Sounded like the first question to ask. And I also asked him if for any reason some part of the prop was outside the water. So yeah, the prop was good, and the prop was in the water and balanced and everything. But I got to talk to his mechanics enough to understand that it's really a high-speed boat, so only half of the prop is in the water as it rotates. So what you have is as simple as this. The shaft goes off the back, and you have the prop. I'm going to make it circular. And it's rotating, but the water level is right about here. And therefore, at each turn, you get a huge bending load in the shaft. And that's what I saw on the fracture here, because what I see is the crack started in the lower left corner right here, and you see all these lines over here up until this point. Call them beach marks sometime. And then eventually right here, there was the final overload. But by the time you had the overload, you already went through half the section almost of that shaft. So it wasn't a crazy high load because it would just bend the whole thing. At the same time, it was a very significant load because after you've gone through half of it, the load was sufficient to break open the other half. And we have some material properties that we use to figure out approximately what that load was right here based on the crack size. And that's also something we'll cover in the class, but I wanted to bring it up right here. There's a blow-up image on the right-hand side. That's your initial flaw size. So it is visible. If I could bring that shaft in, you can see it if you're careful, but it's small. On a 6-inch, it may be 0.5 millimeter. But even at 0.5 millimeter, you can tell that it started from one place and went all around. So that gives us some idea of what's really a bad flaw. This is a bad flaw because we only have one crack that started here. It went all around up to the middle and overloaded. If we had a bunch of small flaws, what will happen right here is you'll have a little circle around here, another circle around here going towards the inside, a little bit like we had with the plastic pipe. That's the big difference. So the flaw size in this case was large. It wasn't so much of a material flaw because there was wear. There was wear between all the gasketing system here of the boat and the outside, and that created that flaw. But we had to go through the process of figuring it, and I thought the flaw size here was something different. This is just an overload, a little bit like we talked about here for shear, except that it's the bending of a shell, and there are welds and everything here, but nothing happens really to the material. It's just changing its shape because it's ductile. So one of the things maybe on the top of the list of figuring out when you design something is it going to be deformable or is it going to be at risk for a fracture without really a change in shape? This was a one-time load. If we had done it 10,000 times, we'll take that pipe out without deforming the plate right here. So it's very important to keep that in mind, that the reason why this is not so much of the geometry that makes this different, it's because there was one overload as opposed to multiple loads. So that's very important to find out when you're designing a product or a structure. How many times is it going to be loaded and unloaded? Sometimes it's easy to find out, sometimes it's not. We'll go with an easy one. It's the front wing of an airplane that extends out for takeoff and landing to create more aerodynamic resistance and get a little bit more of have you seen those? We hear them all the time. We hear the little mechanism for them. It makes a lot of noise, gets people worried. I get worried. There's one of the things that's important about it. It's at the very front, and the aerodynamic there is critical. It needs to be able to extend out for takeoff and landing. It also needs a de-icing system, so you can keep doing your maneuvers even if you have to land on bad weather or take off on bad weather. It's mostly for landing. For takeoff now, they heat things up. They heat the body. So that's how it looks like. You have the skin, aluminum skin. What's in green in this case, the titanium rib. And it's the same rib that has two holes down on the right-hand side. And the big hole here is for air circulation. So they'll bypass the air from the engine exhaust and heat things up when they have to. And that's the main reason for using titanium here as the primary structure as opposed to aluminum. It's a temperature consideration. So we know how many times the aircraft is intended to take off and land as part of the design process. It's actually pretty specific a lot of times. You could have some impacts, but be mostly on the retracted condition where you don't have too many loads. So you have to figure out how you're going to make it into the assembly and resist the environment. And make sure it doesn't crack, right? Because that's what I want to talk to you today was creep and fatigue. So in that specific example with the rib, you have two ways of thinking about fatigue that you may have heard before, maybe in a different way. One is to say, okay, I'm going to make this part real good with no cracks. So I'm allowed to use a smooth specimen, and that's this one here. And I pull on it repeatedly, like we talked about, here with fatigue with a certain loading ratio. And what happens eventually, it will fail. And you generate what we call an SN curve. S for stress, N for number of cycles to fracture. And I can use that data to evaluate if my product is good or not. Well, that's risky. What if I have a big scratch? What if there's a casting defect? Because some of those were going to be cast. Well, that's why in aerospace, a lot of times they use the other approach called crack growth. So that's the lower left. And we put on a crack in the specimen that we test and make sure that even with the crack, it will make it through the entire life. And some people will call it a damage tolerant approach. So on an airplane, you'll see cracks on the aluminum fuselage, but they're okay cracks. They get monitored, they have different sensors with eddy currents, magnetic particle. They go and look at the cracks. When they find one, typically they keep monitoring it. Sometimes they can make a local repair, but a lot of times there's a certain length that's still acceptable because it's built into the design. And that was the case for those titanium ribs for the front fuselage, was because they can't be inspected easily. The way we designed them is we allowed for a crack to exist from the beginning, and through the 30,000 up and down cycle that were anticipated, that crack would not grow to a size that would create an overload fracture. So it was a conservative approach because we could not, we really could not inspect that specific structure once it's all built together with the skin on top and all the rivets in different directions. That's what you've got. You can't do anything about it. So another aerospace example, it would be more the red, are some of the turbine blades. Well, it turns out turbine blades, if you're to say there's a crack in it, it's going to break very quickly. There's so much load on those components that the defects associated with cracks are not acceptable. So it has to be a design on a smooth specimen type approach with more inspection and testing of every piece that's made to make sure that there are no impurities and no geometrical defects. So it will go through very sophisticated surface finishing treatments and very sophisticated casting processes also. So I hope it gives the flavor that depending on what you have to build, you'll use a very different approach. And it may look disconnected, but we'll try to have cases where we actually bring together more than one, because more than one may be governing. So now we're going to go through a few examples that ties back to the class and processing. So we have here, these are SN curves for titanium alloy, and we're looking here at the effect of oxygen content. Well, I mean, look, why oxygen? Well, it gets into the brittleness or non-brittleness of the titanium, so it turns out to be relevant to the cracking of it, and you can see the difference. In one case, you go to a large number of cycles. So when we talk about fatigue life, a lot of time we're going to talk about 10 to the 7 cycles. So we're looking here. And we may have a fatigue life that's about twice as high with higher oxygen content. Well, that tells you that for some of those properties, you have to be careful of your service conditions. It's one of the titanium is actually one of the materials that's very tricky to design for, because people think it's good for everything, but it's not. And I guess these are examples of that. You guys know about grains in metals? Most metals contain a large quantity of grains. It's somewhere typically in the micrometer range. So you have to go to a microscope to see them. It's not like pieces of rocks that you can see it with your naked eye. Oh, I got a grain right here, I got another grain right there. They are very important. They influence a lot of properties, and sometimes in different ways. What we have here is crack growth curve. It's for pure titanium, so it's not an alloy. It's not something we use a lot of times, but it's a good example with those grain sizes here, from very fine to bigger. You very fine here to bigger. You'll change your crack propagation rate. So it turns out big grains here, the black dots, 200 micrometers, are more resistant. And we should go to this here. So when I say more resistant, this is a loading parameter that we're going to cover in this class. It's called the stress intensity. It's close to the stress, but it takes into account crack size. So it's a little bit more complicated. And here you're looking at a crack growth rate on the vertical axis. So for a certain amount of intensity of loading, the finer the grain, the higher the crack propagation rate is going to be. And one way to think of it for this specific case is the crack will have to go longer in certain grain direction and then go longer in another grain direction. If you have big grains, then you have the very small ones. So it's not an uncommon effect for this specific type of cracking to require big grains. And they do that for turbine engine parts, for example. But most of the time, and most of this class, we will want to have small grains for other reasons that we'll talk about. Welding. In general, welding will reduce your fatigue strength, so strength when you cycle the load, by at least a factor of 2. And that's going to vary depending on the condition. The curve here, you can follow it. Yeah, we cover that. So the summary at the end, you'll have it in your notes, but I think we already went through it. Just one word about Friday. Friday, I'm going to go into a summary of deformation concepts that be used both for the life assessment part of the class and also the forming part of the class. So I just wanted to tell you that we're going to be covering the first 3 chapters of the book you were given. Not in all the details, but if you're interested, that's where we're going. I try to keep incorporating examples into it. Everybody know about von Mises? Good? Good. All right. Should be easy.